Welcome back to the next video, everybody. Today's video is on Cartier duality. I won't have much to say today. So what is it? Well, let's suppose G is a commutative group scheme. Then the dual hop algebra from last video, A prime is commutative. And so G prime, which we will use to denote spec of A prime, makes sense as a finite flat commutative R group scheme, and it has the same order as G. So there's this functor that sends G to G prime, right? And this is a contravariant equivalence of the category of finite flat commutative R group schemes with itself. And under the setup, G prime prime is functorially and canonically isomorphic to G, as expected. And so we have a duality here, right? Just like we do in like linear algebra, for example, or in the theory of abelian groups. And this duality is known as Cartier duality, and it vastly generalizes the notion of duality of finite abelian groups, for example. Okay. Now, as discussed in a previous video, the group-like elements of A prime sub B, the base change of A prime to B, are the characters of G prime defined over B. And so it follows from Cartier duality that G is in fact the character group scheme of G prime. And we had a whole video on character group schemes recently. What I mean by that, just to recall, is that G represents the functor that sends B to the group scheme B maps from the base change to B of G prime to the base change to B of the multiplicative group G sub M. And then by symmetry, by interchanging rules, G prime is also the character group scheme of G. So G and G prime, they're character group schemes of each other, right? As you might expect, right? If this is to really generalize what's going on in linear algebra and abstract algebra, that should be true, and it is. Okay, so the last thing I want to talk about briefly is the bracket pairing that we've had come up in the past 2 videos or so. For each R algebra B, the pairing, the duality pairing, G of B cross G prime of B to GM of B, which is just B cross, as you recall, that's given by the bracket symbol brackets of B from above, actually from above, from previous video. If we embed G of B and G prime of B in A prime sub B and A sub B, respectively, as we did above and as we did in the last video. Okay, and so the duality pairing is just given by the bracket, all right? On the other hand, if you view these, you can view these pairings as bimultiplicative invertible functions on G cross G prime over R, which of course is spec of A tensor A prime over R. Right? There's nothing stopping you from doing that, one for each B, right? And if you do that, this function is just, it turns out it's just the identity element in A tensor A prime, which is, as you know, from module theory, that's just R endomorphisms of A. Okay. And what do I mean by it's the identity element there? I mean, it corresponds to the identity map of A. And the reason for this is it's a simple calculation. You just check that bracket lambda tensor F comma ID is nothing but bracket lambda comma F. And that the same holds after base extension. And that exactly gives you what I'm saying here based on the information we've discussed prior. All right. And so I think we're done sort of setting up now the basic theory of finite group schemes, finite flat group schemes in general, all that. And so starting next video, we're going to start pushing towards Raynaud's results that are actually used in the proof of Fermat's last theorem. And so I will see you then, which is tomorrow. And thanks for watching.